An electric charge creates an electric field in the space around it. It also creates a related quantity we shall call an electric potential. This tutorial seeks to explain the concept of the electric potential. It's Kisembo Academy, and thank you for tuning in. Today, we are going to describe what we exactly mean when we say electric potential. In this diagram, we have a test charge. We have a charge Q, which is positively charged. We are also having a test charge. This is in its initial position here. This is a charge Q. Now, initially, this charge was here. This is the initial position of our test charge, which is positively charged. And this charge is within the electric field of this charge, the big one. So this charge Q was moved from this point to that point. Now, if this charge is positively charged, and this charge Q is also positively charged, it means that bringing these two charges, it means will be repelling each other. This will be repelling this charge because this is positive and that is positive. Meaning, for us to be able to move this test charge from this point to that point, it would mean that we will have to do work against this charge because we are working against the repulsive forces of these charges. So it means that work has to be done for us to move this test charge from here to there, because these two are the same charge because of the repulsive forces. So in this case, if work done in moving this test charge we are talking about, which is this, if work done in moving this test charge Q from infinity to some point P near Q is W, then it means that the potential of point Q is given by work done per unit charge. For us to get the potential of this thing at that point, it's going to be that work done per unit charge, which is the potential V. And the SI unit for potential is coming from the formula work done per unit charge. Work is in joules and Q is in coulombs. So it means that the SI unit is going to be joules per coulomb, which is equivalent to 1 volt. So to describe what exactly electric potential is from that background, we shall say that the electric potential at a point in an electric field is simply defined as numerically the work done in bringing a positive charge of 1 coulomb from infinity to that point, and the unit is the volt. So let's look at the electric potential due to a point charge. Here we are having charge at x naught, charge at A, we have charge at x1 at B, and these two, A and B, are separated by distance x, and of course the force is in that direction because they are repelling each other. Now the point charge at A, which is this one, which is Q, is exerting a repulsive force on charge B, that is charge B, and that is why that arrow is pointing in that direction, because they are both positive. This charge B is being repelled in that direction, in the opposite direction. So meaning the repulsive force that exists between this charge and that charge is going to be equal to, the repulsive force is going to be directly proportional to the product of those two charges and inversely proportional to the square of their separation, which is x. So the repulsive force is going to be equal to that. And so we are going to use this to derive the formula for electric potential due to a point charge. If the charge at B is going to be moved towards A by a very small distance, we shall call dx, a very small distance, it means that the work done, the small change in work done, is going to be force times the small change in distance. If charge at B is moved by some external agent by a small distance, we are going to call dx, towards A, where that small distance it has been moved is so small, if considered constant, then the work done by the external agent will be given by that, the change in work. The work is going to be, you know that work is equal to force times distance. So the work is going to be equal to force times distance. Now, if you have to look at these 2 point charges, this is positive and that is positive. So this charge is exerting a repulsive force. So it is pushing this thing away. But our external agent is pushing this charge in the opposite direction to the repulsive force. That is why we are having a minus sign here. It simply signifies that. So meaning the work done is going to be equal to, we substitute for the value of F, So our force is going to be from Coulomb's law, which is Q naught times Q1 over 4 pi epsilon naught x squared times the small element in the distance moved towards the charge. So it means for us to find the work done from 0 to the actual work is going to be, we are going to integrate on both sides. It's going to be equal to work done in moving that charge from infinity to a point R. So it means we are going to integrate this expression with respect to x. So integrating this side will leave us with work is going to be equal to, now if you look at this expression, Q naught times Q1, this is the charge of the charge at A, this is the charge at B. These are both constant terms. 4 pi epsilon naught, all these are constant, so we shall put them outside the integral sign, and we shall only integrate x squared 1 over x squared with respect to x. So when we integrate, this 1 over x squared is the same as x to the power negative 2. We are integrating with respect to that. So from our rules of integration, integrating this is going to be, we add 1 to the power and divide through by the new power, which is negative 2 plus 1. And this is running from infinity to that point R. So we'll end up with negative 2 plus 1 is negative 1, and then negative 2 plus 1 down here is negative 1. So we shall end up with negative x to the power negative 1. So now we substitute in for R here. This negative x to the power negative 1 is the same as negative 1 over x. We substitute in our limits of integration. It's going to be 1 over R. We get that from here. Minus, we substitute for infinity there, negative 1 over infinity. So from here we'll end up with this expression, will end up with negative 1 over R. So this negative and that negative, multiplying these two will give us a positive. So we shall end up with our expression for work as work is going to be equal to Q naught Q1 over 4 pi epsilon naught times R. In this regard, therefore, the definition of potential V at a distance R from a point charge Q in a medium of permittivity epsilon naught is given by that. We have got our expression for work, which is Q naught times Q1 over 4 pi epsilon naught from our derivation, and we are asking ourselves that now from this, how do we come to that? Our V is going to be, it's our potential. Remember from our previous explanation was, it is going to be the work per unit charge. And in this case, we are looking at charge Q1. So it's going to be work, divide that by Q1. But what is work? Work is what we had. This is what we've gotten here. So work is Q naught times Q1 over 4 pi epsilon naught, divide that by Q1, which is the Q1 we have there. So it means that this Q1 and that Q1 are simply going to cancel out. And then we shall remain with our expression. V is going to be Q naught over 4 pi epsilon naught times R. This is our expression for the point charge, of the potential of a point charge in a field, and that is how we come to this. And that is how we conclude by saying that therefore the definition of potential V at a distance R from a point charge Q is a measure in a medium of permittivity epsilon naught is given by that expression. I would encourage you to subscribe to this channel if you want more of these videos, and for the benefit of your colleagues out there that would like to watch this tutorial, simply share. In our previous video, we had just derived V is equal to Q over 4 pi epsilon naught. We explained how it comes about. Today we get to look at a few worked example where we will require to use this. This is Kisembo Academy, and thanks for tuning in. We'll start it off with the first example. We have a point charge, 10 microcoulombs. It is 10 centimeters apart from a point R, and they're asking us to find the potential at point R. So for us to find the potential at point R, we know that V, the potential V, is going to be equal to Q over 4 pi epsilon naught times their separation, which is R. That is going to be equal to, our value of Q is 10 microcoulombs, so it's going to be 10 times, micro means 10 to the power negative 6, then coulombs. So it's 10 times 10 to the power negative 6 coulombs, divide that by 4 pi epsilon naught times R. times the separation. The separation is 10 centimeters, but this separation has to be in meters. So we convert that to meters, and that is going to give us 0.1 meters. So this is going to become, now remember that 1 over 4 pi epsilon naught from experimental observation is equal to 9 times 10 to the power 9, because this is a constant. So it means that this is going to be 10 times 10 to the power negative 6 coulombs. Multiply that by that constant, which is 9 times 10 to the power 9. Divide all that by 0.1. And so our answer is going to be 9 times 10 to the power 5 volts, and that will be our answer. Let's get to the next example. In our next example, they're asking us to find more or less the same thing, only that here our charge is negative. So find the potential at x. Same story. V is going to be that charge Q over 4 pi epsilon naught times the separation, we shall call R. So that is going to be equal to, if we are finding the potential at x, it means the Q, our value of Q is going to be the charge here, which is negative 5 times 10 to the power negative 6 coulombs. Multiply that by the constant, which is 9 times 10 to the power 9. That is 1 over 4 pi epsilon naught. Divide that by R. Our separation is 20 centimeters. Converting that to meters is going to give us 0.2. And our answer there will be negative 225 times 10 to the power 3 volts. Let's look at one more example. In this example, we are having 2-point charges. We are having negative 5 microcoulombs, and we are also having 10 microcoulombs, and they are asking us to find the potential at B. So it means you are going to first find the potential at B due to A. We find the potential at B due to C. Then afterwards we shall find the total potential that is acting on point B. So we will begin. So potential at B due to A, we'll call it VA, is going to be, we'll still use our formula Q over 4 pi epsilon naught times R, and that's going to be, our Q is negative 5 times 10 to the power negative 6. Multiply that by, this is 1 over 4 pi epsilon naught, which is 9 times 10 to the power 9. Divide all that by R, that is 0.1 meters. If we convert the distance of separation here, it is 0.1. So that is going to give us an answer that we've already gotten before, which is negative 4.5 times 10 to the power 5 volts. So let's find the potential at C due to B. So VC is going to be Q over 4 pi epsilon naught times R. That is going to be Q, which is 10 microcoulombs. So it is 10 times 10 to the power negative 6 coulombs. Multiply that by the constant, which is 1 over 4 pi epsilon naught, which is equivalent to 9 times 10 to the power 9. Divide all that by the separation. The separation here is 5 centimeters. Converting that to meters is going to give us 0.05 meters. And the answer we shall get here will be 1.8 times 10 to the power 6 volts. So now for us to find the total potential at B, it means that we are going to add the potential at B due to A, which is negative 4.5 times 10 to the power 5. And we also add the potential at B due to C, which is 1.8 times 10 to the power 6. And then we shall get our total potential. So we go. So meaning that the potential at B, V, is going to be potential due to A plus potential due to C. And that is simply going to be equal to negative 4.5 and our answer here will be 1.35 times 10 to the power 6 volts. And that will give us the potential at B. If you want more of these videos, simply subscribe to this channel, and for the benefit of your colleagues out there that would like to watch this tutorial, simply share this video. In our previous tutorial, we introduced the electric potential. Now we are going to discuss about electric potential difference. Consider this tutorial a continuation of the previous one. It's Kisembo Academy, and thanks for tuning in. If this point has a lower potential and this has a higher potential, so the work done in moving this potential, this charge from a position of low potential to a position of high potential is what we are calling potential difference. In this tutorial, we shall derive the formula of work done in moving this charge from this point to that point. We all know that potential, the unit of the potential is called the volt, and which volt is equivalent to 1 joule per coulomb. So what is the volt? By definition, the volt is simply the potential difference between 2 points when the work done in transferring 1 coulomb of electric charge between the 2 points is 1 joule. And like earlier said, 1 volt is equivalent to 1 joule per coulomb. So let's go ahead and derive the electric potential formula. The potential difference formula. Here we are going to consider a charge Q, and we have also 2 other test charges. Now these charges A and B are lying on a line of force. The line of force is due to this charge Q. Supposing A and B lie on a line of force at a distance A and B separately from charge Q, we are having A lying at a distance A. We are also having B at a distance B. These are points along this line of force, lying on that line. Now when a unit charge is at a distance x from Q, this is the unit charge we are talking about. It is at a distance x from Q. While in free space, then the force acting on it. So now the force acting on this unit charge is we are going to get this force from Coulomb's law of electrostatics, which is going to be 1/4 pi epsilon naught times Q, the product of the 2 charges Q. The Q we are talking about is this charge Q times this unit charge +1. So it is Q times 1 over x squared. So meaning that this unit charge can either move from B to A or from A to B. Now, if this unit charge is to move from B to A, it would mean that it's going to work against the repulsive forces of this Q, because this Q is also positively charged. So it means that work is going to be done against the forces of the repulsive forces of Q. And if this unit charge is to move from A to B, it means that this Q, this charge is going to do work in pushing it away. So now what I'm trying to say here is that the work done, the work that is done against the repulsive forces in bringing B to A is going to be the same as the work done by these repulsive forces in pushing A to B. So we continue with our write-up. Work done on taking the charge from B to A against F, or against the repulsive forces of the charge Q, is equal to the work done, or work which force F will do if the charge were allowed to go from A to B. The force F we are talking about is the force due to the charge Q, the force which we have gotten here as 1/4 pi epsilon naught times that. Now, over a short distance dx, the work done by the force F is given by the small change in work is equal to force times that small change in distance. That small change we are talking about is this. If this thing is to move, this test charge is to move from, let's say, that point to that point, and it is to go through a very small distance dx. So it means that the work done in moving from that, to move through that small distance, is going to be the force times that small change in distance. And that is what this expression means here. Now, what if we wanted to find the work done for that force to move the entire distance? By the entire distance, we are talking about if this test charge is to move from A to B, a significantly very big difference. So meaning that over the whole distance AB, work done by the force on the unit charge, that is work done to move from A to B, is going to be equal to force times distance. So it means you are going to integrate from the point when x is equal to A to the point when x is equal to B. And these distances are the distances from the charge Q, capital Q. So integrating that would give us, we substitute for the value of F, and so it means that work is going to be equal to Q over 4 pi epsilon naught, which is the F we have substituted, multiply that by 1 over x squared. This is Coulomb's law, we've just substituted for F, dx. And it's running from A to B. Now if you realize Q over 4 pi epsilon naught, this is a constant, so we'll put it outside the integral sign, and inside will remain with 1 over x squared. So 1 over x squared is what we shall integrate. 1 over x squared is the same as x to the power negative 2. So x to the power negative 2, integrating x to the power negative 2 running from A to B is going to be equal to x to the power negative 2, we add 1 to the power, and the answer we get here we divide by the whole term, like illustrated here. And so negative 1 plus negative 2 plus 1, here we get negative 1. Negative 2 plus 1, we shall get 1, negative 1. And that's the negative that is going outside here. And so when we are to substitute in our expression here, we are going to end up with negative Q over 4 pi epsilon naught times 1 over x. X to the power negative 1 is the same as 1 over x. It's running from B to A. Substituting B in this expression is going to be 1 over B, minus substituting A in that expression is going to be minus 1 over A. That's the expression we have. So multiplying this negative through these brackets, it would mean negative this times 1 over B and negative this times that. It would mean that this is going to become positive 1 over A. So that's how this comes to this. We have this as positive, which is equal to 1 over A minus 1 over B. And that will be our expression for the work done. If you want to watch more of these videos, simply subscribe to this channel, and for the benefit of your colleagues out there who would like to watch this tutorial, simply share this video. So this is our expression for work done. Work is going to be Q over 4 pi epsilon naught into 1 over A minus 1 over B. But we are interested in finding the potential, not the work done. So how do we get the potential? Remember, in our definition of potential, when we were introducing potential, we said that that potential V is equivalent to the work done per unit charge. We said that potential is going to be work done per unit charge. And remember that this being our work done, when we were deriving this, we were considering a charge Q and another test charge which we called positive 1 coulombs from our diagram. It was Q and the other charge was positive 1 coulombs. So it means that for us to get our value, the potential difference formula, we get it by it's the work done per unit charge, and the unit charge we are talking about here is that test charge Q, which is positive 1. So it's going to be, we substitute for the expression for the work done, the expression that we just got earlier, which is Q times that positive 1 coulomb of charge, divide that by 4 pi epsilon naught times 1 over A minus 1 over B, which is just, this is the substitution for the work done, divide that by the test charge Q, which is positive 1, which is that. So our expression is that, which is this, divide that by 1. And so our potential will end up being Q over 4 pi epsilon naught into 1 over A minus 1 over B. So this is the expression for potential, for the potential difference between 2 points. And our value of A is the distance between Q and A. A is the smaller distance and B is the longer distance. So it means that A, which is the shorter distance, should come first, and then B, which is the longer distance, should come later. Thank you for watching. I would encourage you to subscribe if you want to watch more of these videos. Otherwise, for the benefit of your colleagues that would like to watch this tutorial, simply share the video. In our previous tutorial, we derived the potential difference formula. Consider this a continuation of that as we explore a few worked examples where we will be required to use that formula. We have a question here, 2-point charges, 15 microcoulombs and 7 microcoulombs. We have 15 microcoulombs here and the 7 microcoulombs. Respectively, these are 6 centimeters apart. Find the work done in bringing them 2 centimeters apart. So these two are initially 6 centimeters apart, and now we want to find how much work we will need to do to bring them 2 centimeters apart. So now, for us to find the work done, we need to assume that one of them is stationary. Either assume that the 7 microcoulomb is stationary or 15 is what is stationary. But in this case, let us assume that the 15 microcoulomb charge is stationary and this is the one that is moving, so that the two are eventually 2 centimeters apart. So what are we going to do here? Remember, we said that work done is going to be equal to QV. That is work done. So it means that we're going to have to first find the potential difference. After finding the potential difference, then we shall simply multiply. Then we get the work done. So we begin with our explanation. So we first find the potential V, and from our previous tutorial we derived the expression for potential difference. V is going to be equal to 1 over 4 pi epsilon naught, multiply that by 1 over A minus 1 over B. And we said that A is the shorter distance, B is the longer distance. So what is our value of A in this case? If this thing has moved to 2 centimeters apart, what's the potential difference? So if we are assuming that 15 microcoulombs is the one that is stationary, it means that our value of A is going to be 2 centimeters, which is 0.02 meters, and our value of B is the longer distance where this thing has come from to move from here to here, which is 0.06 meters. So we simply substitute. So if this is the stationary one, it means that it's going to be Q over 4 pi epsilon naught into 1 over A minus 1 over B. So what is our value of Q in this case? Our value of Q is the stationary point, which is 15 microcoulombs. So it's going to be 15 microcoulombs, which is going to be 15 times 10 to the power negative 6 over 4 pi epsilon naught into 1 over 0.02 minus 1 over 0.06. So we shall end up with, now this is going to be equal to 15 times 10 to the power negative 6, multiply that by 9 times 10 to the power 9 into that, and our answer here will be 4.5 times 10 to the power 6 volts. So we continue with getting the potential. So V is going to be Q over 4 pi epsilon naught into 1 over A minus 1 over B. This is the expression for potential difference that we derived in our previous tutorial. Our value of Q in this regard is the stationary point we have chosen, which is 15 microcoulombs. So substituting here is going to be 15 microcoulombs into 1 over 0.02 minus 1 over 0.06. 0.02 is our value of A, which is happens to be the shorter distance, and 0.06 is our value of B, which is the longer distance. And we said that 1 over 4 pi epsilon naught is 9 times 10 to the power 9 according to experimental observations. So it means that 15 times 10 to the power negative 6 over times 9 times 10 to the power 9 into whatever we have here in the brackets is going to give us 4.5 times 10 to the power negative 6. This is the potential difference, V, that we have gotten. So after getting our potential difference, V, now we need to find the work done. The work done in moving this charge from here to 2 centimeters apart, because that is what the question requires. So to get the work done, we know that work done is going to give us Q times V. What is our value of Q? The work done in moving a charge of 7 microcoulombs from this point to that point, so that these two charges are 2 centimeters apart, is going to be the Q, which is the charge in question, the charge that is moving. So it is going to be equal to 7 microcoulombs, which is 7 times 10 to the power negative 6 coulombs. Multiply that by the potential difference, which is 4.5 times 10 to the power 6. And our value of work is going to be 31.5 joules. 31.5 joules, and that is the work done in moving that 7 microcoulomb from 6 centimeters to 2 centimeters. And that brings us to the end of our worked example. I would like to encourage you to subscribe to this channel if you want more videos. And for the benefit of your colleagues out there that would like to watch this tutorial, simply share the video. In this tutorial, we shall discuss the relationship between electric field intensity and electric potential. It's Kisembo Academy, and thanks for tuning in. Let's consider a charge Q. If a charge Q has been moved from point A to point B within an electric field with an intensity E, it would mean that there is a potential difference between A to B, and there is some work that has been done in moving that charge from point A to B. Now, supposing this charge has been moved through a small distance, let's call that distance dx. It means that the work done in moving that charge from A to B through that small distance is going to be equal to force times that small change in distance. Now, for us to substitute for the value of F, the force, it will follow. We'll get it from the formula for intensity. Remember, we said that intensity is the force per unit charge in the field. So it follows that from the definition of electric field intensity, intensity E is the force per unit charge. And so if we are to make F the subject of the formula, it would mean that F is going to be E times Q. And we said that that negative is going to be as a result, because the charge that is being moved, it is working against the repulsive forces, the other 2-point charges. So it means that we substitute this value of F in that point. And so it means that our new value of work, hence the work is going to be E times Q, which is that, times the small change in distance. And that will be our first relation, or our first equation. So now we have another expression for work, which is work is Q times V. If the potential difference between A and B is dV, where B is at a higher potential than A, then in terms of potential difference, it means that work done is going to be the charge of that, the charge times the change in potential difference, and that is going to be our second expression. So what we do, we equate these two expressions. Work done here is equal to that. The work done in terms of potential difference is that. So it means that it is this expression is equal to that expression, and that is what has been done down here. The work is going to be equal to the work. So the expression, the first expression, equation 1, is going to be equal to the second expression. And if you divide both sides here by Q times dx, Q and dx, this dies with that, and then this goes with that. You remain with our intensity as being equal to change in V over change in X, change in potential difference over change in the distance. So this is the relationship that exists between electric field intensity and potential difference. So to note, NB, dV dx is the rate of change of PD with the distance in the electric field, which is also the potential gradient at that point. So where does this leave us? It gives us an expression that in uniform fields, therefore, intensity is going to be equal to the potential difference with the potential difference, divide that by the distance. We have two large horizontal plates that The upper plate is positively charged and the lower plate is negatively charged. From the relationship between electric field intensity and electric potential, we were able to discover a relationship that if we are to find the electric field intensity in between these two plates, that electric field intensity would be equal to the potential difference between that field and the distance in between. And when we are looking at two plates like this, it is as simple as this is a uniform field, and looking at this uniform field, we know that the intensity that exists between this uniform field is going to be the potential difference between these two plates, divide that by the plate separation, and this plate separation in this case has been denoted by D. We shall look at a worked example. We have two horizontal plates. These two horizontal plates are 2 centimeters apart as shown in the diagram. Two horizontal plates are 2 centimeters apart and they are in a vacuum, and the upper is maintained at a positive potential relative to the lower plate. Now, the upper is maintained at a positive potential relative to the lower plate, so that the field strength between them is 2.5 times 10 to the power 5 volts per meter. So it means that our value of E here is going to be 2.5 times 10 to the power 5 volts per meter. That is the meaning of that. So they're asking us to find the potential difference between the plates. So what is the PD between these plates? The potential difference between the plates, we know that our intensity E is going to be potential difference V over D. So meaning that to find our potential difference V is going to be equal to E times D. What is our intensity? Our intensity is 2.5 times 10 to the power 5. So that's going to be 2.5 times 10 to the power 5. Multiply that by the plate separation, which is 2 centimeters. Our plate separation being 2 centimeters, we convert that to meters. And so it's going to be 0.02 meters. So it's going to be 0.02 meters. And our potential difference between the plates is simply going to be 5.0 times 10 to the power 3 volts. If an electron charge of 1.6 times 10 to the power negative 19 and mass of 9.1 times 10 to the power negative 31 kilograms is liberated from rest at the lower plate, find the speed of the electron on reaching the upper plate. These are our two plates. We are having an electron here, and it is being liberated towards the positive plate, and they are asking us to find the speed by which it is liberated from rest, from this lower plate to the upper plate. So let's get one thing here, that when this electron here, it is having a charge, it is an electron, meaning that it is negatively charged. If it is negatively charged, it is definitely going to be repelled from this negative plate, and it is going to be pushed towards the positive charge as a result. So while it is moving up, at first it has electric potential energy. So as it is moving up, this electric potential energy, while it is in this field, is being converted into the kinetic energy with which it is going to use to move to the upper plate. So it means that from the law of conservation of energy, we know that energy can neither be created nor destroyed, but it is but can be changed from one form to another. So it means that the electric potential energy that was possessed by this electron while it was in the field has been converted into the potential energy with which it is moving towards the plate. And so that is our first step, that the electric potential energy has been converted, or it is going to be equal to the kinetic energy of the electron. And the electric potential energy here is, which is actually the work done, is QV is equal to the kinetic energy with which the electron moves, and that is going to be a half times the mass of the electron times the velocity with which it moves, v squared. So making u the subject of the formula, because we're interested in finding the velocity with which it moves, u is going to be equal to the square root of 2 times the charge times the potential difference between the plates, divide that by the mass. So it's going to be 2 times the charge on the electron, which is 1.6 times 10 to the power negative 19, times the potential difference, which is going to be 5.0 times 10 to the power 3. We got this potential difference in our previous, because it's a continuation of this. It's 5.0 times 10 to the power 3 volts. Divide that by the mass. The mass of the electron is a constant that was even given in the question, which is 9.11 times 10 to the power negative 31. And we end up with our answer as 4.2 times 10 to the power 7 meters per second. And that is the velocity with which it moves. This brings us to the end of this video. Thank you for watching. I encourage you to subscribe if you want more of these tutorials. Otherwise, for the benefit of your colleagues out there who would like to watch this tutorial, simply share this video. Thanks for watching and hope to catch you in the next tutorial for Kisembo Academy. This is Arnold Rangakuramia.